The previous lectures, we understood what will be the effect of a 90-degree excitation pulse followed by acquisition. We also saw the module where you had a tau 180 tau module followed by the 90-degree pulse and what is its influence on the overall scheme of matters. And this tau delay is kept constant before and after the 180-degree pulse. I felt that as we go forward, it might be a good idea to introduce Fourier transformation a little bit in order to make things easier for us to understand. I presume a lot of you would have learned what is Fourier series. A Fourier series is one where a periodic function f of x can be expressed in terms of sinusoidal function such as cos function and the sine function. It's given as a series expansion as shown here where an, a0 and bn are coefficients that will be determined as shown below. So we are talking about a periodicity of L for a given function. So for instance, if you're talking about a sinusoidal function, L will be 2 pi because that is its periodicity. In this case, A0 is going to be determined by this integral 2 by L from minus L by 2 to plus L by 2 f of x dx. And similarly, an is going to be determined by 2 by L integral minus L by 2 to plus L by 2 f of x cos nx dx. And similarly, bn will be given by 2 over L integral minus L by 2 to plus L by 2 f of x sin nx dx. And what you are able to understand here, you can talk about any periodic function and you are able to understand these coefficients would be determined by these integrals as shown here, and the functions that represents the f of x right now will be the sine and the cos function. Without going into much detail in this, one is able to understand that the cos nx and sin nx can be represented in terms of e power I nx, where this f of x can once again be written as a summation that goes from minus infinity to plus infinity Cn e power I times 2 pi by L times n times x, where the Cn integral would be given by 2 over L minus infinity to plus infinity f of x dx. And what you are able to understand here is that in the Fourier series, you can only go integer numbers, meaning you can go 1, 2, 3 and so on. You cannot have a number between 1 and 2. And also it is restricted by the fact that the function that you are trying to represent has to be periodic. In the condition that there is no periodicity, that is when L tends to infinity, the whole thing can be represented in terms of a Fourier transform, which is what is used in NMR spectroscopy, because you can never be sure whether the frequencies that you are looking at are only integral steps. They can be any chemical shift, any frequency that you might end up getting. So we are going to write something equivalent to what we had seen for the Fourier series expansion, where the S of omega, this is the frequency domain spectrum. Remember, we are talking about an omega terms because we like angular frequency in the field of NMR spectroscopy. This will be given by the integral between minus infinity and plus infinity S of t times e power minus I omega t times dt. So this is called a Fourier transform. And this capital S of omega and small s of t are actually called Fourier pairs. Meaning, if you know what is S of t, the time domain signal, you can get the frequency domain spectrum. And conversely, if you know the frequency domain spectrum, you can also calculate what should be the time domain signal. So for instance, this is the time domain signal, which is FID. Remember, so far we have been writing S of t as, let's say, summation over m plus of t. So that's the signal we are talking about. Alright. So if you want to get the time domain signal, this will be given by 1 over 2 pi minus infinity to plus infinity S of omega e power I omega t d omega. So therefore, S of t can be used to get the frequency domain spectrum S of omega and if you do inverse Fourier transformation, you will get the time domain signal. This is nothing but the FID. This is the frequency domain spectrum that we want to see. The reason why I once again came back to the whole point of Fourier transformation is because if your signal is of the form e power I omega t, remember this is the term that we ended up getting finally when we took the trace of I plus times sigma in a simple one-dimensional NMR experiment. We will also see other cases as we go forward so that we understand what ends up coming. If your time domain signal is given by e power I omega t, then the frequency domain spectrum, which when you Fourier transform using the transform that is shown here, you are going to end up getting a Dirac delta function at capital omega, which is the chemical shift that you want to determine, minus the variable, that is the omega variable. So for students who might not know what's a Dirac delta function, let me plot it for you here. This is a function when omega is equal to capital omega, you get 1, and when omega is not equal to capital omega, you get 0. So therefore, if you want to plot this as a function of small omega, you are going to get a single line with no line width at plus omega. So therefore, when omega is equal to omega, you are going to get the whole function as 1. So you end up getting it as 1 here, and you don't get any other signal anywhere else. So let's continue this discussion further. The next example that we took in terms of NMR spectroscopy was that, okay, you still had a 90Y pulse followed by acquisition. In addition to chemical shift, we also understood in this case where there is a scalar coupling associated. In that moment, if you recollect, the product of the I plus times the density matrix and the trace that we wanted to get from this turned out to be e power I omega t times cos pi j t. And we said this is going to give a spectrum centered at capital omega plus minus pi j. We will see how that ends up coming. Remember, this is a time domain signal. You got to Fourier transform this, and we already know Fourier transformation of e power I omega t. Now you are multiplying it with the e power pi j t. So why don't we rewrite this function e power I omega t times cos pi j t. Cos pi j t can be rewritten as 1 over 2 e power I pi j t plus e power minus I pi j t. The whole function ends up being e power I times omega plus pi j times t plus e power I omega minus pi j times t the whole divided by 2. And if you might recollect, when you do Fourier transformation of e power I capital omega t, you get a Dirac delta function at capital omega. This is what we just saw a moment back. So therefore, when you Fourier transform this entire beast, you are going to get similar to what you had seen before. Now omega is transformed to omega plus pi j. This is going to end up being omega plus pi j minus small omega plus. Once again, you have the omega here, just that it's slightly different. Capital omega minus pi j minus omega the whole divided by 2. So therefore, wherever you started earlier, which had just a single resonance at plus omega, now introduction of J coupling, all it ends up doing is still not give any resonance apart from omega, but just that you're going to get omega plus pi j and omega minus pi j, and it's weighted by a 1 over 2, so you're going to get 0.5 is to 0.5. So this helps you understand that if your e power I omega t is modulated by another sinusoidal function, it just results in a splitting centered around the chemical shift by pi j in this example. If your time domain signal is given by exp I omega t times sine pi j t. Previously we saw cos pi j t. This can also be decomposed into 1 over 2 I exp plus I pi j t minus exp minus I pi j t. So the only difference that you are able to see here is that previously you had e power I omega plus pi j times t plus e power I times omega minus pi j times t divided by 2. Here the sign gets changed, and also the I will be present. Let's not worry about I, that can just be a phase factor. For now you don't have to worry about it, we will understand that later. So what you end up seeing here is that you have 1 over 2 I exp I times omega plus pi j times t minus exp plus I omega minus pi j times t. So therefore this is going to give you 1 over 2I times delta at omega plus pi j minus small omega minus delta omega minus pi j minus omega. Therefore, if you plot this right now, once again, only when omega is equal to omega plus pi j, this part will give you a signal, and only when omega is omega minus pi j, this second part will give a signal. So, but however, it has a 1 over 2 and a minus sign. So what you will end up getting is something of this sort. This is omega, omega plus pi j, omega minus pi j. So this will be 0.5 is to minus 0.5. The minus comes up because you have a negative sign here. As we go forward in further lectures, you are going to end up seeing signal that will be of the functional form exp I omega t times sin pi j t, or for that matter e power I omega t times cos pi j t. And therefore, from Fourier transformation, you are able to understand all the cos modulation ends up doing is to split this into a doublet with the magnitude as given by whatever modulation that you end up getting. So that's all we have seen so far, and we will be using this as we go forward to take a look at the spectrum that we will generate for different kinds of experiments.